So next question. In this video, this is the first question. If all triangles are right angle, then no triangle is equiangular. Here also I am dividing the statement into two parts. First part is P of x. P of x represents x is a right angle triangle. Q of x represents x is an equiangular triangle. So right angle triangle everyone knows, I think so. If there is an angle 90 degrees, then it is called right angle triangle. Equiangular triangle means here if the angle is here 60 degrees, here also 60 degrees, here also 60 degrees. This is called equiangular triangle. S is the universal set consisting of all triangles. So, observe the given sentence I am writing as symbolic form. All is there. That's why for all x belongs to S. Here S is universal set which consists of all triangles. Here no not is there. That's why simply I am writing P of x. For then I am writing implies no triangle is equiangular. No is there. That's why I am writing negation of Q of x. So this is the symbolic form of given statement. So already we know this one. Here I have written in terms of P and Q. We already discussed in terms of A and B. So this is A, this is B. We are writing A as it is. That's why I am writing for all x belongs to S, P of x. And is there, and is as it is. Next, negation of Q is there. So I want to write negation of this. Negation of for all x belongs to S, negation of Q of x. So we already know the negation for all is there exist. Negation of x is Q of x. That means this indicates the negation of given statement. Now I am writing this symbolic form as words. Here for all is there. That's why all. P of x is triangles are right angle. That's why I am writing triangles are right angles. And is there. I am writing and. There exist indicates. Replace there exist with some. Q of x is triangles are equiangular. That's why the negation of given statement is all triangles are right angles and some triangles are equiangular. So we move on to next question, that is write the following proposition in symbolic form and find its negation. So this is the given proposition. We want to write first symbolic form. After that we want to convert. We want to find out negation. So here all is there. So first of all I am going to split the sentence into two statements. First is P of n. Second is Q of n. Here in the statement only n is there. That's why I am writing P of n, not P of x, Q of x. So observe, I am taking P of n as n is divisible by 2. I already told, even though here not is there, when I am taking P of n or Q of n, I am not considering this not. Q of n is odd. The symbolic form of given statement is, here for all integers n is there. For this one I am writing for all n belongs to z. Here not is there. That's why I am writing negation of P of n. Here no not. That's why I am simply writing Q of n. So this is the symbolic form of given statement. Now I want to write negation of this. I already told for all becomes there exist. N belongs to Z as it is. Negation of this. Again we use the same thing. What is that one? Negation of A implies B is identically equal to A and negation of B. Here A means negation of Pn, B means Q of n. So A is as it is, that is negation of Pn. Here and is there, that's why I am writing and. For the second portion, I want to put negation. This is the second one. That's why I am putting negation of Q of n. So this is the symbolic form of negation of given statement. Now I am going to write this as this in word form. Negation is there. That's why not will come. So their exist is there. That's why some integers n belongs to z means n is an integer where n is not divisible by 2. Why not means because negation is there. That's why introduce not in the P of n statement. Then it becomes n is not divisible by 2. And again negation is there. N is odd becomes n is not odd. So this is the negation of given statement. Next we move on to next statements. Write down the following prepositions in symbolic form. Here only we want to write symbolic form. No need to convert the given statement as no need to write negation of given statement. Observe the first question. Some integers are divisible by 7. Some indicates there exist. Integers is there. That's why x belongs to z. Are divisible by 7. So z is set of integers. So p of x is x divisible by 7. Second question. All real numbers are complex numbers. So here real numbers means I am taking x belongs to R. All is there. That's why for all R indicates set of all real numbers. Then the statement becomes x is a complex number. I am replacing this with x is a complex number. There is third question. There is an integer which is not a perfect square. So there is there. Instead of there is, I am writing there exists. Integer is there. That's why x belongs to capital Z. Not is there. That's why negation of p of x. I need p of x. P of x is now x is a perfect square. Not means negation of p of x. Z indicates integers. Again negation formation problems are there. Write down. Some rectangles are squares. Here S denotes set of rectangles. In this set, some rectangles are squares. P of x is rectangles are squares. So sum is there. That's why there exists x belongs to S. No negation. Not is not there. That's why I am writing P of x only. Now I need negation of this symbolic form. There exist becomes for all. X belongs to S as it is. P of x open statement becomes negation of P of x. Now convert this symbolic form into word form. For all is there. For all means we can write all or every. Every rectangle. Not is there. Not a square. Negation of rectangles or squares is rectangles are not squares. Here I am writing every. That's why I am writing singular verb. All youngsters like cricket and some elders like football. Now I need negation of this statement. S is set of people. P of x is youngsters like cricket. Q of x is elders like football. Here no not is there. But here all is there. Here some is there. All replaced with for all. Some replaced with there exist. And replaced with and. This is inverted V. So this is the symbolic form of given statement. Now I need negation of this. For all becomes there exist. P of x becomes negation of Q of x. And becomes or there exist x becomes for all x. Q of x becomes negation of Q of x. So I want to replace this as sentence form. That is, their exist is there. That's why I am writing some youngsters do not like cricket. Negation of this is do not like. Are is there. That's why are I am writing. Here elders like football is there. Negation of this one is all elders do not like football. While writing this form, you can check the English grammar because here S is there means we want to write do. If here S is not there, we want to write does, like that. Okay, after writing this sentence, once you read and reframe the sentence grammatically. So this is the next section of the chapter, Introduction to Proofs. So we want to prove a statement means we require some axioms and some theorems. With the help of axioms and theorems, we are going to prove some mathematical statements. So here the same thing written. There are different methods to prove the theorems, statements. So first method is direct method. So in the direct method, observe a direct proof of a conditional statement. Conditional statement means P implies Q only is constructed assuming that P is true. So we are going to prove, we want to take P is given statement. We want to prove Q. So while proving this statement, we are going to use some axioms, definitions, already proved theorems. With the help of axioms, definitions, previously proven theorems, we are going to get Q. That means we start with P and use axioms, definitions, previously proved theorems. We get Q. That's why P implies Q. P implies Q is a conditional statement. So observe here one problem is there. Now we are going to find this problem. If x is an integer, if x is an integer, that means x is that to even integer. X is an even integer. That means this is P. We want to prove x square is even integer. This is Q. So by considering P, we want to prove Q. So observe the sentences. P is x is an integer. Q is x square is an even integer. So the hypothesis is P. If x is an even integer, then by definition of even integer, x can be written as 2 into some integer. For example, 4 is an even integer. 4 can be written as 2 into 2. Here 2 is again an integer. Minus 4 is also even integer. Minus 4 can be written as 2 into minus 2. Minus 2 is also again integer. So here observe x equal to 2m for some integer m. This is general form of even integers. Now I need x square value. Now x square equal to, substitute x value here. Then we are going to get 2m square. 2 square is 4, m square is m square only. So 4m square can be written as, we got the value of x square as 4m square. 4m square can be written as 2 into 2m square. This is again integer. If a number can be written as 2 into some integer, then it is called even integer. That's why x square can be written as 2 into 2m square. So x square is even integer. So here we assumed P, we proved Q. Second question. Here also we want to assume if portion, we want to prove then portion. Here a and b are odd integers, then a plus b is even integer. So by considering this and also known axioms, definitions, previously proven theorems, we want to prove a plus b is an even integer. So I am taking this as p, this as q. So an odd integer is of the form. Add odd integers can be written as 2k plus 1. But here k is some integer. So given that a is odd integer. That's why a can be written as 2m1 plus 1. Here m1 is integer. B is 2m2 plus 1. So m2 is also an integer. Now I want to add these a and b, that is 2m1 plus 1 plus 2m2 plus 1. Again I am writing these two terms first, that is 2m1 plus 2m2. 1 plus 1 is 2 only. Again observe 2 is common in each term. Take 2 outside, m1 plus m2 plus 1. So a plus b is written as 2 into something. That's why a plus b is an even integer. That means we considered p, we proved q. Next method is proof of contraposition. So here you can observe proofs that do not start with hypothesis. That means in the previous case we start with p, we end at q. But here we are not starting at p and end with conclusion. Even though we are not starting with p, we end with conclusion q, are called indirect proofs. One of the indirect proofs is proof by contraposition. In this method, the conditional statement P implies Q can be proved by showing that it's contrapositive. Contrapositive, I already told. The contrapositive of P implies Q is negation of P implies negation of Q is true. So if we once observe, actually we want to prove P implies Q is true. But instead of proving this, we are going to prove negation of Q implies negation of P is true. Whenever this is true, automatically this one is true. So basing on this concept, we are going to solve one problem now. Observe, prove that if n is an integer, then 3n plus 2 is odd, then n is odd. So here observe, n is integer and 3n plus 2 is odd. So this is P portion, this is Q portion. So observe, this is P, this is Q. So I need negation of Q implies negation of P. The negation of n is odd is n is not odd. For implies, I am writing then negation of P. Negation of P is 3n plus 2 is not odd. So assume that n is even. Actually we want to prove n is odd. But I am taking n is even. If n is even, n can be written as 2 into some integer. Here k is integer. Substitute this 2k value in the place of n. Then I am going to get 3n plus 2 becomes 3 into 2k plus 2. So 3 2s are is 6k plus 2. So take 2 common. After taking 2 common, we are going to get 3k plus 1. Observe, here I am writing 3n plus 2 as 2 into some integer. So this is even number. Whenever this is even number, this is also becomes even number. But at the starting, what we considered 3n plus 2 is, observe, contrapositive statement. Once again, I am telling 2 into something means this portion is even number. If this portion is even number, this is also even because these two terms are equal. So, therefore, the contrapositive statement, if n is even, then 3n plus 2 is even, is true. So, whenever contrapositive is true, its original statement also true. Here I told, whenever this is true, this is also true. That's why the given statement is true. In the given statement, what we have, n is odd. That's why finally this problem is solved. Proof by contradiction method. Contradiction means we want to prove one statement. We are going to prove this by contradiction method. So once observe, instead of proving the statement is true, we assume that the statement is false, which leads to contradiction by the end of the proof. This concept I am going to explain by taking one problem. Show that root 2 is not rational number. Actually, root 2 is a rational number. That's why show that root 2 is not a rational number. So, root 2 is actually irrational number. So, this is irrational number. Irrational number means it is not a rational number only. So, observe, actually we want to prove root 2 is not rational. But what we are going to assume? Root 2 is rational. We know that rational numbers are numbers which we can write in the form of p by q. That's why root 2 can be written as p by q. Here again p and q are no common values. So p and q are different. The different means here p and q are not like this 4 by 2. Because if 4 by 2 means 4 can be written as 2 into 2. That's why P and Q have no common factors. We are not considering like this. We are considering like this. Here 3 and 2 is there. 3 and 2 have no common factors. But 4 and if we consider 4 and 2, 4 and 2 have common factors too. In this case, we are considering root 2 equal to P by Q. P and Q have no common factors. Like 3 by 2. Now squaring on both sides. Root 2 whole square equal to p by q whole square. So root 2 whole square, root and square get cancelled. We are getting 2. I am writing 1 square for p, 1 square for q. P square by q square implies p square equal to 2 into q square. Here again observe, I am writing p square as 2 into q square. A number which can be written in the form 2 into something, 2 into some integer means it is even. So, this is even number. That means whenever RHS is even, LHS is also even. So, finally we can say that p square is even. If p square is even means p compulsory even. P is even. So, P is even means P can be written as 2 into some integer. That means P equal to 2m. Again do squaring on both sides. So, we can write P can be written as 2m. Substitute this P equal to 2m here. This one, in this one, then becomes P square is there. P square means 2m whole square. In RHS, I am writing as it is, that is 2q square. 2 square is 4. 4m square is equal to 2q square. Cancel 2 1s are 2 2s are. Then you are going to get q square equal to 2m square. So 2 into something means this is even number. When this is even, this is also even. So q square is even. Whenever p square is even, p is even. Like that only. Q square is even means q is even. So p and q have common factor 2. P is even means p can be written as 2 into something. Q is even means q can be written as 2 into something. So p is having 2 as a factor, q is having 2 as a factor. But at the starting, we considering p and q have no common factors. But after doing all this process, what we get? P and q have 2 as common factor. That means this is contradiction to our assumption which we made at the starting. That's why root 2 is rational number. Root 2 is not a rational number. Not a rational number means it is irrational number. Next by proof by counter example. Counter example means if they gave one sentence, we want to prove that one. But instead of proving that one, we give one example that statement is false. So observe, to show that a statement of the form for all x, p of x is false, we need to find a counter example k such that p of k is false. If we give one example, then the proof is completed. That is called proof by counter example. So observe, one question is there. Every positive integer is the sum of squares of two integers is false. We want to give one. If we give one example satisfying this statement, then the proof is completed by using proof by counter example. So now I need one example which satisfies this statement. So observe, to show that the statement is false, let us take particular integers, that is not the sum of sum of the squares of two integers. Let us take here positive integer there. For this one I am taking 3 sum of squares of two integers. So observe, a square plus b square, sum of squares of two integers. And automatically a and b are integers only. So as a square and b square value should be less than 3. So observe, here we have 3. Observe, one example I am going to give. 5 equal to 2 plus 3. That means 2 is less than 5. 3 is also less than 5. In the similar manner, a square is less than 3. B square is also less than 3. Observe, whenever we write the sum of two numbers as single term, then 2 is less than 5, 3 is less than 5. In the similar pattern, a square less than 3, b square is also less than 3. Only values that can be taken are, so this statement is true only for the values if we take a equal to 0, b equal to 1. So a square equal to 0, by means 0 square is 0, b square is 1 square is 1. Substitute these values here. 3 equal to 0 plus 1. RHS value is 1. LHS value is 3. That means 3 not equal to 1. When we take A equal to 0, B equal to 1, this one is not true. This is called counter example. Next one is proof by method of strategy. In this section, we will learn some tricks of finding proofs by working backward and adopting existing proofs. This one I will do in the next video.